Right, in this video, we're going to talk about 9.3 with the integral test and P-series. These are suggested homework problems for this section. In number one, I'm going to give you a different answer than the book is going to give you, and I'll explain why to the best of my ability. You're kind of going to need to see me use this different definition in the problems that we work, and um, then hopefully you'll understand that this is going to give you some, you'll draw the same conclusion. It won't change anything about convergence or divergence, but it'll give you different answers for the integrals. I'll explain what's going on here. So what are the conditions that have to be satisfied for the integral test? So the easy part is to say condition one is continuous, and the book is going to say on 1 to infinity. I'm not. I'm going to say some capital N to infinity. And we're going to have to say, positive, continuous, on this same interval, and 3 is decreasing. Positive, continuous, and decreasing are the three things that we need. So what do I mean about capital N? So what I mean by capital N is for all n greater than or equal to some capital N, where capital N is an element of the natural numbers, and n is greater than or equal to my lower bound a that starts with my integral f of x is positive on this. So say given integral a to b, or I'm sorry, a to infinity, f of x dx. So normally this is going to say 1 to infinity in your book. I want you to know that the lower bound does not have to be 1. It just needs to be a finite number. And it needs to be a finite number so that these three conditions are met. Now, your book's not going to care because it cares about the limit existing, and that's going to happen whether I include the area from 1 to n or not. But technically, these conditions are only met once I reach my maximum and start to turn back down. So I'm going to use that maximum value n, and I'm not always going to use the number 1 like the book does. So positive, continuous, and decreasing are three things, and we must show those three things every time that we want to use the integral test. We don't get to use the integral test without showing that the function is positive, continuous, and decreasing. Your teacher is going to tell you whether it's acceptable for you to just sketch a graph and use your calculator to say this, or whether you need to show some things with sign charts and derivative tests, or whether you have to do direct comparisons of things between the nth term and the n+1th term. Your teacher will tell you exactly how to do this. I'll show you a couple of different methods throughout the homework just so you're exposed to all these different options. I will more heavily favor a particular option, and hopefully you'll figure out which one I like without me telling you, but I definitely think that there's a best option for me. So anyways, let's go ahead and look at number 2. Since 2 is an even problem, you won't have any answers for it, but determine whether the series is a p-series. So a p-series is something that's in the form of n equals 1 to infinity of 1 over n to the p, and it converges if p is greater than 1. It diverges if p is less than or equal to 1. So there's no ambiguity here. This has a rule that says it converges in one case and it diverges in the other case, and there's no ambiguity here with this rule. So we love this rule for p series. So 2a, is this a p series? Yes, it is. N is equal to 1.4, which means that it converges. Now, p needs to be a positive number for a p series, right? Because it needs to be, this n to the p needs to be in the denominator. It can't be a negative exponent and come across the fraction bar. So no, this one is not, because this one would turn into n equals 1 to infinity of n squared. That's not a p series, because it's not 1 over n to some power. 3, yes, it's a p series. N is equal to 3, and that would converge. Okay, let's look at number 3. And we'll be using the integral test first, because it's the only way that we can really prove the p series test to be true. So that's why we have to use that first. This is going to be one of the ones that you want to use less often than other tests when given the choice, just because it has these conditions that must be shown. So remember that n is greater than or equal to 1 here. 1 is always positive, and therefore I'm going to have a positive number in the denominator. A positive divided by a positive is going to be positive, because it was positive over a positive is a positive for all n greater than 1. Let's go ahead and graph 1 over x plus 3, and we'll take a look at this. Zoom 6, and it's a rational function like that. So I'll sketch a graph of it, say that we know that it has a vertical asymptote over here at -3, a horizontal asymptote at 0. It has a y-intercept here at 1/3, and that it comes down like this, and that at 1/4 we are positive, continuous, because rational functions are continuous on their entire domain. And the only place where it's discontinuous is at -3. So we've met condition 1, positive on 1 to infinity, continuous on 1 to infinity. Now you can look at the graph and you can say that it's decreasing, but how are we sure that it never comes back up over there? So I don't like this graph method to tell me about whether it's decreasing or not. I also don't really love it to tell me whether it's positive or continuous, because I can only see one part of the graph. I can't see all of it, so I prefer something like sign charts or derivative tests or something more conclusive. I may even use a direct comparison or something like that here. So let's look direct comparison wise. Let's look at 1 over n plus 1 plus 3. And let's compare that to, is this going to be less than 1 over n plus 3? So 1 over n plus 4, is that less than 1 over n plus 3? It certainly is, because the numerator stayed the same and the denominators got bigger. Let's pretend we didn't know that. There's a rule here that says if we take the reciprocal of both sides, that the direction of the inequality sign will change. Then I'm going to subtract n from both sides, and I'm going to see, is it true that 4 is greater than 3, that's true. So this is true. So this is true. So this is true. Because this last statement is true, all the statements above it here that led to it were also true. And it's true that an plus 1 is always less than an, which means that it's decreasing. So decreasing on the entire interval 1 to infinity. So now that I've shown that it's positive, continuous, and decreasing, I'll set up my integral from 1 to infinity of 1 over x plus 3 dx. Notice I changed my n's to x's when I set up my integral, because n really is going to be a discrete values over the natural numbers of n is 1, and it's a solid dot, or n is 2, and it's a solid dot, n is 3, and it's a solid dot, but it's not all these connected things in between. As soon as I change to x, x is any real number here in the interval, and it connects all the dots, and I want that smooth curve like that, that is going to be differentiable at all these points, and so on, so, and integrable. So let's go ahead and let's evaluate this. Now, I'm not going to do the thing from chapter 8 where I put in the dummy variable for b here and take the limit as b goes to infinity. We understand at this point what it means to have a limit at infinity. I'm just going to go ahead and write it in the form of ln of x plus 3 from 1 to infinity. If your teacher says don't do this, don't do this. But at this point in the class, most teachers are going to say, yeah, I understand that you understand that you can't really plug in infinity, and that this is a limit, and that you need to know that you need to take the limit as you go to infinity, not that you're plugging in infinity. So the limit as x goes to infinity of ln of the absolute value of x plus 3 is infinity, minus ln of 1 plus 3 is 4, and infinity minus any finite number is going to go to infinity here, and the integral diverges. And it diverges by the integral test. So by the integral test, summation from n equals 1 to infinity of 1 over n plus 3 diverges. Because the integral diverges, the series diverges. If the integral converged, the series that's related to it would converge. This goes all the way back to Riemann sums and how there's a relationship between infinite series and definite integrals. So this one's not really definite, it's improper, but you get the idea that they're related concepts. The area under the curve can be written with an infinite series, and they both do the same thing, that if the infinite series converges, the integral will converge. If the integral diverges, the infinite series will diverge, so on. Let's look at number 7. Summation from n equals 1 to infinity of e to the negative n. So that's going to be e to the negative x, which we know what that looks like, that that's a function that is always decreasing, that it's always continuous, and it's always positive. So positive, continuous, and decreasing. This is just one of those parent graphs that I don't really feel a lot of need to put a lot of effort into telling you that it's positive, continuous, and decreasing, because you know what the function y equals e to the negative x looks like. So let's go ahead and set up the integral now. 1 to infinity of e to the negative x dx will be a negative e to the negative x, and that's going to be evaluated from 1 to the limit as we go to infinity, right? I'm just going to write that. So as I go towards infinity over here, e to the negative x goes towards 0. Negative e to the negative x will also go towards 0. Then I change my sign and I add. I get e to the negative first is equal to 1 over e, which is a finite number L. And so the series converges by the integral test. Let's look at 11. We have the series 1/3 plus 1/5 plus 1/7 plus 1/9 plus 1/11 plus dot dot dot. And I'm just going to say plus 1 over 2n plus 1, where this is n equals 1, n equals 2, so on and so forth. Here that this is my pattern for my nth term here. So this is equal to summation from n equals 1 to infinity of 1 over 2n plus 1. So 1 over 2x plus 1. If I look at that, this should be positive, continuous, and decreasing for all n greater than or equal to 1. Positive, because this is a positive number, divided by that will always be a positive number. Continuous, because the only discontinuity is going to be at n is equal to negative 1/2, which is not within my domain here of 1 to infinity. And decreasing, so I'll show you a way to tell that it's decreasing here that I haven't done yet. So if f of n is equal to 2n plus 1 to the negative 1, f prime of n is equal to a negative 2n plus 1 to the negative 2 times 2, or a negative 2 over 2n plus 1 quantity squared. And for my first derivative from 1 to infinity, again, the only interesting number that might make the numerator or denominator 0 is negative 1/2. I'm past that, so just pick a number that's greater than 1, like 2, negative 2 over 4 plus 1 is 5, squared is a negative 2 over 25 is a negative number, and decreasing, it's never going to change sign because there are no zeros of the numerator or denominator within this interval. So it's definitely positive, continuous, and decreasing on the interval 1 to infinity. Integral 1 to infinity of 1 over 2x plus 1 dx, and I'm going to fix this for my u du substitution, where I multiply by 2 in the top and 1/2 on the outside to balance it out. So this will be 1/2 ln of the absolute value of 2x plus 1, evaluated from 1 to infinity, is going to approach ln of infinity is infinity, minus 1/2 ln of 3, and that's going towards infinity, and this diverges by the integral test. So let's look now at number 15. 15 gives us summation from n equals 1 to infinity, ln of n over n squared. And ln of n needs to have n greater than 0. N can't be equal to 0 here, so my domain definitely would be 0 to infinity. But I wouldn't be positive on ln of n until I was greater than 1. So that's what I already have there. So positive on that interval. Once I'm past 1, that's correct. Not when I'm equal to 1. Is it continuous on that interval? It is, because it's going to be continuous on its entire domain. Is it decreasing on that entire interval? The answer is no, it's not. So let me show you on the graph here, and then let me show you what I'm going to do to work this problem out in a slightly different way than what the book would do. So zoom 6. So I don't know if you can see it, but it goes up and it reaches a maximum, and then it starts to come back down towards the horizontal asymptote. I'm going to zoom in here really close, from 0 to 10 on x, and then I want negative 1/2 to 1/2 right now on y. And you can see that a lot better there, that it goes up to a maximum and comes back down. So second calc maximum, and I need the next whole number past this maximum value, or the x value where this maximum happens. So the maximum happens at 1.6487224 approximately. So I need, it's only going to be decreasing for all n greater than or equal to 2. Now let's see if I can figure that out with a derivative or with some kind of comparison. I don't really like comparisons with logs, so I'm going to use a derivative here. And that's derivative of the top times the bottom minus derivative of the bottom times the top, all over the bottom squared. That's going to be n is n times 1 minus 2 ln of n over n to the 4th will be f prime of n is going to be 1 minus 2 ln of n over n to the 3rd. Now n to the 3rd is always going to be positive, so I'm interested in 1 minus 2 ln of n is equal to 0, so that's at negative 2 ln of n is equal to negative 1, ln of n is equal to 1/2, n is equal to e to the 1/2. If I come to e to the 1/2, second e to the 1/2, and there's my number that I just got from my calculator. So I need to go for the next number, the next integer value above e to the 1/2. That's called a ceiling. That's what this notation is going to be equal to 2, and that's going to be my capital N that I'm going to use for my lower boundary here of ln of x over x squared dx. So I'm positive, continuous, and decreasing on 2 to infinity. Now, why can I do that? Because this right here is the same thing as if I just pull this first term out and find ln of 1 over 1 squared, which is 0. It's not always going to be 0, but it's going to be a finite number there, and make this n equals 2 to infinity, ln of n over n squared. I haven't changed the convergence or divergence of the problem at all, because this finite number of terms out here that I pull off is just a constant that doesn't change. If this goes to infinity, infinity plus a constant is still going to be infinity. If this goes to negative infinity plus a constant is going to be negative infinity. If this is a constant plus a constant, it's going to converge to some number. But convergence or divergence does not depend at all on this finite number of terms that I've peeled off here. It depends entirely on this infinite series portion right here. And so just because of the way that the definition requires positive, continuous, and decreasing on an interval here, then I need to make sure that that interval ensures positive, continuous, and decreasing, and the interval from 1 to infinity does not assure positive, continuous, and decreasing, because if we look at the graph here from 1 to the square root of e, I'm actually increasing. So that's why I'm giving different answers than the textbook might, in terms of what the value of this interval is going to be, why I changed my lower bound, but it's not going to change the convergence or divergence of the integral or the series, because we only differ by a finite number of terms, and that doesn't change anything. So now let's look at how we would calculate this. I'm going to use integration by parts. U is equal to ln of x. dv is equal to 1 over x squared, or x to the negative second. dx du is 1 over x, or x to the negative first. dx and v is equal to a negative x to the negative first. So we have u v, so a negative x to the negative first, ln of x. And again, I'm not really allowed to plug in infinity, but I'm going to write that anyways. You know what that means. Minus the integral of v times du. So this is going to be this is a negative ln of x over x from 2 to infinity, which is an infinity over infinity situation where I could use L'Hopital's rule. Now I know that ln of x is the slowest growing function that we know about right now, and that linear function is going to grow faster, and that means that this is going to go to 0. I'm going to prove that to you with L'Hopital's rule, though. So this is plus integral from 2 to infinity of x to the negative second dx. So this is going to be negative. And then using L'Hopital's rule, this is 1 over x over 1, which is the same thing as 1 over x from 2 to infinity. That's going to go from negative 0 to positive 1/2 plus x to the negative first from 2 to infinity is 1/2 plus 0 minus I can't stick that into L'Hopital's rule. I need negative limit as x goes to infinity of ln of x over x. That's where I use L'Hopital's rule, plus ln of 2 over 2. Plus x to the negative first, 2 to infinity. This is going to be negative limit as x goes to infinity of 1 over x, which is going to go to 0, plus ln of 2 over 2 plus 0 minus 1/2 ln of 2 minus 1 over 2, which is a finite number, and this converges. I almost did some bad math there. You can't stick your non-infinite limit into L'Hopital's rule. Split it up before you use L'Hopital's rule so you don't make that mistake. So again, note that the work in CalcChat is going to be different. In your student solutions manual, you're going to get a different answer here for this number. You're not going to get a different answer for the convergence or divergence of the series. Let's look at 21. Summation from n equals 1 to infinity, n over n to the fourth, n to the fourth plus 1, and positive over, that's always positive, so positive is taken care of. Continuous is good because there are no discontinuities here. And what about decreasing? X over x to the fourth plus 1. Zoom 6. Sure looks like I have a maximum value there, right? So second calc, maximum, and so that's 0.75 something. So 1 is bigger than that, so it's going to be decreasing, positive, continuous, and decreasing on 1 to infinity. Let's go ahead and see if I can establish that it's decreasing for you, though. I think positive and continuous are pretty straightforward. Derivative, though, is derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared equals n to the fourth plus 1 minus 4n to the fourth over n to the fourth plus 1 quantity squared. And so that's going to be equal to a negative 3n to the fourth minus 1 over n to the fourth plus 1 quantity squared is equal to a negative square root of 3n squared minus 1 times square root of 3n squared plus 1 over n to the fourth plus 1 squared, and that root 3n squared plus 1 doesn't factor anymore, but I end up with a fourth root of 3 times n plus 1 and a fourth root of 3 times n minus 1 times a square root of 3n squared plus 1 over n to the fourth plus 1 quantity squared. And let me pick a large enough number here so that I'm sure that we are going to get a positive times a positive times a positive. So I need n to be greater than 1 over 3 to the 1/4 power. So 1 divided by 3 to the 1/4 power is going to be 0.7598, so on. So the ceiling of 1 over 3 to the 1/4 power is going to be equal to 1, which is fine. So I'm positive, continuous, and decreasing on 1 to infinity. Let's go ahead and find my integral from 1 to infinity of n over, I'm sorry, x over x to the 4th plus 1 dx. I'll write 1 to infinity of x squared squared plus 1 squared. And then I want u is equal to x squared. Du is 2x dx. So this is 2 and 1/2. A squared is 1, a is 1. So this is going to be equal to 1/2 arc tangent of x squared evaluated from 1 to infinity, arctangent of, can't really say arctangent of infinity, but the right end behavior of arctangent approaches y equals pi over 2, the left-hand side of arctangent approaches negative pi over 2. So this is 1/2, and then the limit as x approaches infinity of arctangent of x squared, since infinity squared will be infinity, is this right-hand side over here. That's going to be pi over 2 minus arctangent of 1 is pi over 4. So this is 1/2 of pi over 4 is pi over 8. And that's going to converge. Let's go ahead and look at the next problem, which is 27. And we're asked to see which conditions for the integral test fail here. So summation from n equals 1 to infinity of sine n over n squared. Well, this is going to, this is not going to be always decreasing for some number. This is going to be oscillating. Let's go ahead and look at this just to be sure, but sine of x over x, quantity squared, zoom 6. This is zoom out. We can't really see it. Let me zoom in instead. So zero to 10. And let's make this scale here go between 0 and 1 by tenths. So it's going to be going up, down, up, down, up, down, and the hills are going to be getting smaller and smaller. If I didn't zoom in here, you wouldn't be able to see them, but it keeps oscillating like this. So, and I could prove that to you with a derivative test pretty easily, that it keeps going positive or negative, positive, negative, positive, negative, so on with the sine chart. But this is not, how did I say this? Oscillating behavior. There is no value of capital N for which f of n is decreasing for all n greater than or equal to capital N. Okay, so that's a hard one to see with a calculator. Let's look at number 31. Summation from n equals 1 to infinity, 1 over n to the 0.9. And we're asked to use the integral test to determine the convergence or divergence of the p-series that's here. So this is a p-series, but we're going to look at 1 over x to the 0.9. What does that look like? Zoom 6. That looks positive, continuous, and decreasing to me. So definitely positive that 1 divided by a positive number here is positive. Continuous because the only bad number is going to be 0, and that's not in my interval. Decreasing, we can prove that with a simple derivative here. We want to be sure that f prime of n, this is n to the negative 0.9, will be negative 0.9, n to the negative 1.9 is negative 0.9 over n to the 1.9, and this denominator is going to be positive for all of these values here. So I have a negative divided by a positive is a negative. So it's going to always be decreasing. And that's going to be from on 1 to infinity. Will be good. So we set up our integral test 1 to infinity of 1 over x to the 0.9 dx. And so this is going to be integral 1 to infinity of x to the negative 0.9 dx. I'm going to add 1, which is going to be 0.1, and divide by 0.1. And then this is 1 to infinity is going to be infinity to the 10th root of infinity is still infinity, minus 1 over the 10th is 10, which is still going to infinity, and this diverges. So let's look now at 35. 35 says to use the p-series test. So 1 plus 1 over, I'm going to call that 2 to the 3 halves. I'm going to call this 3 to the 3 halves, and 4 to the 3 halves, and 5 to the 3 halves, plus dot dot dot, plus 1 over n to the 3 halves. And this would be 1 to the 3 halves as well down here. So that will be summation from n equals 1 to infinity, 1 over n to the 3 halves. And so 1 over x to the 1.5 is 3 halves. Zoom 6. And it again appears to be positive, continuous, and decreasing. Let's check that out to be sure. So positive divided by a positive is a positive. Continuous for all x greater than 0. decreasing. And let's establish that f of n is equal to n to the negative 3 halves. F prime of n is a negative 3 halves. N to the negative 5 halves is equal to a negative 3 over 2 to the 2 times n to the 5 halves. And n to the 5 halves will have to be positive. 2 is positive. Negative 3 divided by that positive number is going to be equal to a negative number, meaning that this is going to be decreasing on 1 to infinity. Set up my integral test. 1 to infinity, 1 over x to the 3 halves dx is equal to integral 1 to infinity, x to the negative 3 halves dx, the x to the negative 1 half times negative 2. Limits of integration will be 1 to infinity. It's negative 2 times 0 plus 2 times 1 is going to be 2. And this is, why did I do this with the integral test? I don't want to do it with the integral test. I want to do it with the p-series test because that's easier. Let's skip all this hard stuff with positive, continuous, and decreasing since it's a p-series. P is equal to 3 halves, which is greater than 1. So it converges. That's how easy it was supposed to be. I wasn't supposed to do all that work. Let's look at 47. Now you know how you would prove it, though, with the integral test. Now we want to find the particular p-value for which this one converges. So n equals 1 to infinity of n over 1 plus n squared to the p. So we already had a problem earlier. I think. No, we didn't do it. It's like a problem we did earlier, but we would have a problem if p is equal to 1, that we would end up with a natural log here because we would have du over u, and that we've seen that the natural log problems, when I take ln of infinity, I get infinity. So it will diverge for p equals 1. And I know by definition, p has to be greater than 0. And I'm going to skip p equals 1. So starting with p equals to 2, I'll go ahead and look at this situation of 1 to infinity of x over 1 plus x squared to the p, where p is greater than or equal to 2, I think. So 2 and 1/2, 1/2 of, this is u to the negative p du, where u is equal to x squared plus 1, 1 squared plus 1 is 2, and infinity squared plus 1 is infinity. So this is going to be 1/2 of u to the 1 minus p over 1 minus p, evaluated from 2 to infinity for u. So 1 as long as p is greater than 2, 1 minus p is negative, and this first part is going to go to 0 minus 2 to the 1 minus p over 1 minus p is going to be equal to a negative 2 to the negative p over 1 minus p, which is going to be a number, and this converges for all p greater than or equal to 2. Now, I didn't really show you that this was positive, continuous, and decreasing, but it is because there's always going to be some value of n here, some capital N, for which this will be positive, continuous, and decreasing. There will exist n greater than or equal to capital N for every such series like this, where p is greater than or equal to 2, for which f is positive, continuous, and decreasing. It's just going to shift to the right as I go along here. So let me show you that this, if this is x over 1 plus x squared, then the graph of this is going to go up one time and then come back down, and it's right there. If I make this to the third power instead, then it still has that kind of a up and down in it. Y equals, let's change this to a 100th power. I can't see it so easily, but if I zoom in here and make this between negative 0.25 and 0.25, you can see that little peak in there, and it comes back down. So it's always going to do that. It's always going to have that shape. Where exactly that peak is up for grabs, but there's always going to be this capital N for which it's going to be positive, continuous, decreasing, and head towards that horizontal asymptote of 0. So because of that, I can say that the p-series idea here for this problem is going to be that it will converge for all p greater than or equal to 2 for number 47. And it will diverge for all p that are greater than 0 and less than or equal to 1. All right, let's look at number 73. '73 says that the summation from n equals 0 to infinity of 2/3 to the n. This is just a review problem. What test do we use? This converges by the geometric series test. R is equal to 2/3, which is less than 1, so it converges. for 79, we have summation n equals 2 to infinity, 1 over n, ln of n raised to the third. Let's take a look at this. 1 over parentheses x, parentheses ln of x raised to the third power, and then close parentheses, close parentheses. We'll get rid of all this stuff over here. Zoom 6. So for n greater than 2, it certainly looks like it's positive, continuous, and decreasing there. Let's go ahead and establish that though. Positive. This will be a positive number for ln of 2. A positive cubed will be positive. Times a positive is positive, and a positive divided by a positive is a positive. So condition 1 is met. Continuous, it's going to be discontinuous at 0 and at 1. So we're past all those places. So continuous for sure on that interval from 2 to infinity. And then decreasing, let's see what we can do to establish that this is decreasing on the interval from 2 to infinity, or do we need to pick another number for that? So first derivative test here is going to give me f of n is equal to n to the negative first times ln of n to the negative 3. So f prime of n is a negative n to the negative second ln of n to the negative third plus a negative 3 n to the negative first ln of n to the negative fourth times n to the negative first. F prime of n is a negative n to the negative second ln of n to the negative third minus 3 n to the negative second ln of n to the negative fourth. So f prime of n is equal to a negative n to the negative second ln of n to the negative fourth will be a ln of n minus plus 3. And this will be f prime of n is equal to ln of n plus 3, negative out front, n squared ln of n raised to the fourth. So ln of n plus 3 will be positive, n squared will be positive, ln of n raised to the fourth will be positive. So this is a negative divided by a positive will be a negative, and it will always be decreasing on 2 to infinity. So positive, continuous, and decreasing on 2 to infinity. And then we can make this 2 to infinity of ln of n to the negative third times, let's make that an x, times 1 over x dx will be a ln of x to the negative second times a negative 1/2. And then this is from 2 to infinity will be infinity to the negative second, that'll go to 0. But 0 plus 1/2 to the ln of 2 to the negative second is 1 over 2 ln of 2 squared. So this converges by the integral test. And that's it for this video. We'll come back next time and talk about 9.4, which is direct comparison and limit comparison tests. See you for the next video.